Hey guys, the objective of this video is to look at the graph for the circular foundation and look at what A on H on A is compared to A on H, because that's on the same axis. We're going to see what that is in a second. Then we're going to do an example for final and initial settlement of a circular foundation. We do that by finding A on H or H on A. We find V, the Poisson's ratio. That'll either be given to us or we're going to have to work it out. We're going to find IP, which is from the graph. We'll then find the average pressure, and then we can find the final settlement or the initial settlement, depending on what we're looking at. So let's just discuss this A on H, H on A. So that is one of the axes of the graph, and it's on the same axis, so it can be a bit confusing. But all it is A is equal to the radius of our circle, and H is equal to the depth of the layer. So it's the layer depth. So say if we had A radius of 10 meters, and H a depth of 4 meters. If we were to work out A on H, so A on H would equal 10 on 4, which would be 2.5, whereas H on A would equal 4 on 10, which is 0.4. So if we come across to our graph now, which value would we use? So we have A on H equals 2.5. A on H, so you can see 2.5 isn't in the range from 0 to 1. That's in the red, where 1 is common between H on A and A on H, whereas H on A equals 0.4, H on A equals 0.4. So that is in the range for H on A, which means that we'd have to use H on A as the value. This in contrast to, say, our A equaled 3 meters and our H equaled 6 meters. So A on H would equal 3 on 6, which equals 0.5. and H on A would equal 6 on 3, which equals 2.0. So A on H equals 0.5. So A on H, 0.5 is within that range, whereas H on A, 6 on 3, 2. So 2 is not in the range, it goes from 0 to 1 of H on A, which means we'd have to use A on H. So at the end of the day, there's just there is a spectrum of values for each case, H on A or A on H, and only one case for the values you're given will match that spectrum. So in the question, you just need to make sure you test both of them and see which one matches. So that is just, we're going to be using this in a second now. It might seem a bit weird what we're doing, but all we're doing is we want to find H on A or A on H such that it falls within the spectrum so that we can use this axis to find some values. So let's move on to our example now. So we're first going to find the final settlement. So the final settlement is what we're finding first, and this is what we're given. We're given a force on our circular foundation is equal to 600 kilonewtons. We're given a diameter of our circle is 6 meters. We're given the depth of the layer is equal to 10 meters. And E dash equals 5 MPa and V dash equals 0.3. So we need to introduce a formula for settlement. Settlement equals PAV, which is the average pressure, times by A, which is the radius, times by IP, which is a factor we find from our graph, all divided by E. So if I define this on the side, PAV is the stress, A is the radius of our circle, IP is from the graph, and E is the modulus of elasticity, so mod E, so the modulus of elasticity. So you can see that we're going to find final settlement now. So we know as soon as we see the word final settlement, we know that we have to use the E dash and V dash values, because it's a final settlement like we discussed in the previous video. So let's go and find all these factors. Let's first find the average pressure. We know that stress is equal to force on area. So we can find our stress. We're given a force of 600 kilonewtons. So 600 divided by the area, which would be pi by the radius. So the diameter is 6 meters, which means the radius would be 3 meters. So pi on 3 squared. That's the force on the area. And we would get a value of 21.22 kPa. So we found the average pressure. We know that A is equal to 3 meters because A is the radius of the circle. So we've got those, and we know that for our case, E is E dash because we're doing final settlement, and E dash is equal to 5,000 kPa, being consistent with our units. So now we need to find this IP term, which is from the graph. So for IP, we first need to find H on A or A on H. So we have A equals 3 meters, and our depth of layer is 10 meters. So if we were to go find this, we would get 3 on 10. So A on H would equal 3 on 10. So which is 0.3. So we'd come to our graph, and we would find, so A on H is 0.3, A on H down here, 0.3 is between 0.2 and 0.4, and we know that the V value we're using is V dash, which equals 0.3, which was given in our question. So V dash is 0.3, so we're going to use these two values. So 0.3 is A on H, so that's around there, which I've marked in red, and we're going to go up to V dash, which is 0.3. So here's 0.2, 0.4, 0.3 is somewhere between there. So we'll roughly go up from here to here, go across, find our I value, which is roughly 1.0. So I equals 1.0, which means we have all the information to find our settlement. Settlement equals PAV times A times I, all on top of E. So we know that the pressure we found to be 21.22 kPa. So 21.22 by the radius, which is 3, by the I value we found, which is 1.0, and this is all divided by E. And E in our case, because we're doing, once again, final settlement, which is the drained values. So we're doing final settlement where we have to use the E dash and V dash, which is drained. So E dash is given to us as 5 MPa. Just being consistent in units, that's 5,000. So we can go and work this out. We get 21.22 by 3 by 1 divided by 5,000, which is 0.0127 meters, which is 12.7 millimeters. So that's how you would find the final settlement. If you wanted to find the initial settlement or the immediate settlement, it's going to be the exact same process, except we can no longer use E dash and V dash. We have to use VU and EU because it's immediate, which means that it is undrained compared to the final settlement, which is drained. So we need to find EU and VU. We know VU is always 0.5, but we need to find EU. So we're going to use that formula we saw in the previous series where EU equals 3E dash on top of 2 outside of 1 plus V dash. So this would be 3 outside of, our E dash was 5 MPa, so 5,000 kPa, on top of 2 outside of 1 plus, our V dash in the question is 0.3. So on top of 0.3, if we were to work this out, we get 5,769 kPa. Okay, so we can now go and find our IP for this value. So we know VU is 0.5. Our A on H is not changing, that's still the same. The dimensions of, and that's because that's dependent on the dimensions and depth of our case, which is the exact same for this question. So the only thing that's changed is the V, which now is 0.5. So we're going to come up, I'll do this in blue. So we're going to come up from here to 0.5, which is there, and then we're going to come across. That's about 0.62, call it. I equals 0.62. Just a heads up as well, this graph, I sort of did it on Photoshop and drew it myself. So if you're using a proper graph, you're going to get different values to me. The process is the exact same though. So I equals 0.62. We know that settlement equals PAV by A by I on E. So the average pressure is still not changing. It's the exact same case. So it's 21.22 kPa times by the radius, which still is not changing. But the I value we found is now different. That's 0.62. And this is all divided by E. And this is now the E of the undrained because we're doing initial settlement, immediate settlement. So the E undrained we found is 5,769. If we work this out, 21.22 by 3 by 0.62 divided by 5,769, we get 0.0068 meters, which is equal to 6.84 millimeters. So, in this question, just to recap, we found the final settlement and the immediate settlement. To find the final settlement, the equation of settlement is the exact same in both cases. However, when you find IP for final settlement, you have to use the drained conditions, which is E dash and V dash, when you use this graph. For the immediate settlement, it's undrained, which means we need to use V subscript U and E subscript U. And once again, the process is the exact same. The only difference is E dash and V dash and EU and VU for the immediate and final settlement. Hope that helps, guys.